Hello people, welcome back. I'm Manish Wagle and this is my YouTube channel. And today we are continuing our instrumentation first series. In previous video, we did the introductory class to the instrumentation system and learned about the basic of instrumentation system. And in today's class, we are starting the theory of measurement. And as the class progresses, we will dive deeper into the instrumentation system. Before starting today's class, I would also like to say that all the links to other classes and the slide will be available in the description below. And if you have any questions related to the topic, please feel free to comment down so I can help you or suggest you. Also, if you liked the class, then please consider subscribing and sharing the video because it will motivate me creating new content. Now, without any delay, let's start today's class. The theory of measurement. At first, let's see the topics which we are going to cover in this lesson. Here we have the introduction, static performance parameters, dynamic performance parameters, errors in measurement and its analysis, measurement of voltage and current, measurement of low, high and medium resistance, AC bridge and measurement of inductance and capacitor. But in this video, we are only going to cover introduction, static parameters and dynamic parameters. And in future video, we will continue from errors and complete the chapter. Now let's move toward the introduction. At first, let's talk about measurement. Measurement is an act of comparison between the unknown physical quantity and its predefined standard known quantity in order to find the value of unknown quantity. To have a proper measurement, the measured value must be error-free. To have an error-free measurement, the user must know the operation and characteristic of the instrument they are using and the cause of the error in the measurement. So, theory of measurement is basically the study of characteristic of the instrument, errors and their analysis, and the way to minimize and control the error in the measurement. Now let's move toward static performance parameters. Static performance parameters are those criteria of measurement system which must be considered when an instrument is used to measure a condition which does not vary with time. Here are the list of some static performance parameters, but those which we will be covering in this video are accuracy, precision, sensitivity, resolution and linearity. Now let's talk about the accuracy. Accuracy is the closeness with which an instrument reading approaches the true value of the variable being measured. Deviation from the true value indicates how accurately and measurement has been done. Accuracy can be expressed in following three ways. There are point accuracy, accuracy is percent of scale range, and accuracy is percent of true value. The point accuracy is the accuracy of the instrument only at one point of its scale. It does not give any information about the accuracy at any other point on the scale or in general the accuracy of the instrumentation system. For instrument of uniform range, its accuracy can be expressed in terms of scale range, although it is highly misleading. For example, if we have a thermometer of range 100 degrees Celsius and have an accuracy of only 1% of scale range and it measures 20 degrees Celsius, then the error will be as high as 5%. Whereas accuracy as percent of true value is the best way of expressing accuracy, as it uses true value of the quantity being measured. For example, if you have a thermometer having accuracy of 1% of its full scale reading of 100 degrees Celsius is used to measure 20 degrees Celsius, then the measured value will be 21 degrees Celsius or 19 degrees Celsius with the error percent of 0.05%. Now, precision is the measure of reproducibility of the measurement. It composes of two characteristics, conformity and the number of significant figures. The difference between accuracy and precision is that if an instrument gives a result that is highly repeatable, but far from its true value, then the instrument is precise but inaccurate. For measuring 5 degrees Celsius, 4.99 degrees Celsius can be considered accurate, whereas 4.998766 degrees Celsius is a precise value if the measured value is repeatable. For sensitivity, it is the ratio of magnitude of output signal or the response to the magnitude of input signal of the quantity being measured. When calibration curve is linear, the sensitivity of the instrument will be constant. When the calibration curve is not linear, the sensitivity varies with input, that is, sensitivity equals small change in output upon small change in input. You can see the same in the graph below. Resolution is the smallest change in input value to which the instrument responds. If an input is given to an instrument and is slowly increased, it is observed that the output does not increase immediately. Rather, it increases after certain increments. Those increments are called resolution. For analog instruments, it is the smallest division in the scale, whereas for digital instrument, it is the least significant bit. Linearity is the measure of maximum deviation of any of the calibration point from the straight line. It is given by the equation of slope as y equals mx plus c, where y is output given by the instrument, x is input given to the instrument, m is slope, and c is intercept in the output axis. Now that the static parameters are done, let's talk about dynamic performance parameters. Dynamic performance parameters is the characteristics that is used to study the behavior of the system between the time that the output value changes and the time the value has settled down to its steady state value. Different characteristics of dynamic performance parameters are speed of response, response time, measurement lag, frequency response, bandwidth, dynamic error, signal to noise ratio, damping factor, rise time, settling time. But in this video we will only focus on speed of response, response time, measurement lag, frequency response, and bandwidth. Now let's quickly go through all of them. At first, speed of response indicates how fast the input given to an instrument brings the output. Response time is the time required by the system to settle to its final steady state after the application of input. Frequency response is the plot of gain with respect to the frequency. It is of two types: gain versus frequency and phase angle versus frequency. This both in combined also known as Bode plot. Measuring lag is the delay in the response of an instrument to the change in measured quantity. It is of two types: retardation type and time delay. And in retardation, the response of measurement system begin immediately after a change in the measured quantity has occurred. Whereas in time delay type, the response of measurement system begins after a dead time after the input is applied. Now the last property we have is bandwidth. It is the frequency range over which an instrument is designed to operate the output after receiving the input signal with constant gain. It is calculated by the gain versus frequency curve of the instrument. Its unit is Hz and is given by BW equals F2 minus F1 Hz, where BW equals bandwidth, F1 equals minimum frequency, and F2 equals maximum frequency. With this, we completed our today's targeted topics. In next video, we will continue from error in measurement and its analysis. So I hope you learned something new today, and if you like the content, then please like and subscribe. Thank you.